All right, so here is the first of three problems associated with uniform probability density functions for continuous random variable. And it's a problem that, if we chose to, we could literally dispatch in 10 seconds. But as I said a couple of times in the Canvas module writings, these uniform continuous distributions, they're not terribly useful in applications. I won't say they're totally useless, but they're not terribly useful in applications, but they're great teaching tools, particularly trying to get you to see this relationship between areas underneath curves and probabilities. And that connection you're making use of over and over again in the problems that are assigned in these areas. So actually this connection was there back in the previous chapter when we were looking at discrete probability distribution functions. And let me take a second to remind you of that. Let's think of one particular discrete probability density function, or as you'll see, mass function, and that's associated with tossing two coins and keeping track of how many heads occur, right? When you toss two coins, you'll get heads, 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 tails, tails, heads, tails, tails. There's 4 outcomes, yeah? So if this is the random variable, and that is in this case number of heads, and we'll call it x, then x can take on, in this experiment, 0, 1, or 2, right? You can have 0 heads in the outcome tails, tails. You can have 2 heads in the outcome heads, heads. And you can have 1 head in the outcomes first coin head, second coin tail, and the other outcome first coin tail, second coin heads. So what we can do in this distribution, we called it a frequency distribution function. We just called it a frequency distribution table, really. Okay. What we're doing is we're assigning, since there are 4 outcomes and only one way in which you get 0 heads, the probability of its occurrence is 1. Likewise, 4 outcomes, only one way to get 2 heads, probability of occurrence is 1/2. But 2 outcomes out of the 4 give you 1 head. There's the table. This is also known as, we didn't call it this, but this is also called a probability mass distribution or function. Okay? And you might see that as PMF. All right, what it does is it assigns a probability to the occurrence of an event. Yeah, this 1/4 is the probability assigned to a 0. We can show this graphically, right? If I go ahead and I plot this in a histogram form, let me just draw the form first. It would look like this. Yeah, where this is 1/4, dot, 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 and this is 1/2, and this is 0, 1, 2. This is the PMF for this particular experiment of tossing 2 coins. Yeah, so at this point what you need to look at is there's something that's very convenient here. And what's convenient is if I kind of arbitrarily say the width of this little rectangle, and I've done something visual, so let's take advantage of the visual aspects. If I just call this width 1, then the width times the height of each one of these blocks is the probability. Yeah, the probability that 2 heads comes up exactly is the width times the height. This is 1/2, yeah. And that is sort of conveniently the probability. The probability mass function is the assignment of what the probability of occurrence is to those numbers. And really conveniently more than anything else, the area underneath the curve associated with each one of these discrete numbers is the probability of its occurrence. And furthermore, the total area underneath the curve, P0 plus P1 plus P2, is equal to 1, as it should be. When you throw those two coins, one of four things is going to happen, right? There are four possible outcomes. Or if you're keeping track of the number of heads, there are three possible outcomes. You get 0 heads, you get 1, or you get 2. You're going to get one of those things. You know, if you don't, time stops and matter falls apart. So this is just the statement that with certainty something is going to happen. And visually you can connect that to the total area under the curve is 1. Under, dot, 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 the curve, where by the curve I mean the PMF, is equal to 1. Yep. So we sort of worked around that, and that's the case. Now, so what we do here conveniently, when we turn to the chapter page, or the page from the previous chapter to the chapter in now, we went from discrete to continuous probabilities. What we're going to do is kind of bring this very same concept along with us, that the areas underneath the curve are associated with the probabilities of occurrence. Now, there's a subtlety here that occurs. Let me jump to the problem that we were given. The problem we were given says that all of the numbers, the continuous numbers between 690 and 850 have an equal probability of occurrence. Okay? This function that I've just drawn, as I've moved from discrete to continuous, takes on a different name. This is a PMF, this is a PDF, a probability density function. But it serves the same purpose as the probability mass function of assigning to values a probability of occurrence. There's just a catch. And the catch is that while up here I can find the exact value for 0, exact value of probability for 1, the exact value of the probability for 2. I can do that here as well too, but they're all 0. And you can see why actually pretty simply. If you pick any one value here, what's the probability of its occurrence? Well, up here, it's that value divided by the total number of outcomes, right? And values, there's one of these, there's two of these, there's one of these, and there's 4 outcomes. Over here, continuously, there's one of these, but there's an infinite set of possible outcomes, you know, an infinite set. We move from a sample space that's finite to a sample space that's infinite. And so all of the probabilities of exactly one number are 0. That's why you have to talk in terms of ranges. This particular problem says, what's the probability that the random variable that we reach into this distribution and pull out is greater than 790? Well, again, here's the rub. We would like it to be the answer to that question, we'd like to be the area underneath the curve here. And the area underneath this curve, so if this is the probability that x is greater than 790, notice now I'm not dealing with a particular value, I'm dealing with an interval. There's the interval I'm dealing with right there. That probability is, again, the area of this rectangle, which is 850 divided by 790. Well, let me leave it like that for a second, and divided by this total range. I'm sorry, I wish I had done this a little differently. Okay, so that's 60 all over 160, and that's 0.375, the answer to the question. I think I'll cover what I'm wanting to say right now in problems to come here. Okay, let's move on to the second problem.